In this video, we are going to handle one specific example, and we're going to calculate the expectation of XL and the expectation of XP for two very special distributions. In this example, we have X and Y. X follows an exponential distribution with parameter lambda. In fact, lambda is 1. By the way, in our textbook, the density is lambda times e of negative lambda x. This may be different from other textbooks, maybe even different from the SOA syllabus. Well, they probably use 1 over lambda. So in this case, the expectation of an exponential is 1 over lambda. In many textbooks, it will be lambda, because they use 1 over lambda to replace lambda here. Okay, the second distribution we consider is for y. Y follows a log normal. This is the notation from the textbook. My notation is to add another calligraphy n to denote this is log normal. Okay, the meaning of log normal is if you take log, I use ln, the book maybe use log, LLG. So basically, ln and LLG, they mean the same thing, both the natural logarithm. This follows a standard normal. So that's why the name is log normal. That's when you apply a log transformation on y, you will get a normal distribution. So these are the two distributions we have. We want to study everything for these two, okay? Exponential is very easy because in order to calculate the expectation of XL, what we need is the survival, right? And survival function for exponential, it's simply exponential of negative lambda x. In this case, is negative x because lambda is taken to be 1. Okay, so that's why we have this formula. The expectation starts from d, 0.25 is the deductible. So from d to infinity of the survival function, the inside part or the integrand is the survival of your x. This is a very easy calculus question. Right? I actually would like you to write one more step. So the antiderivative is negative of exponential negative x. And then we write a vertical line to denote x goes from d to positive infinity. When you plug in positive infinity, you get 0 minus negative e to negative d. And then you get e to negative d. Again, give me all the details when you submit your homework or exam. That helps me to quickly identify whether you know everything or not. The survival function, obviously we just plug in the d for 0.25, you get the survival probability, and then from E of L, you divide by the survival probability, you get E of P. So E of P or E of XP will be the expectation of XL divided by the survival probability at the deductible. So it's very easy to see. This is 1. It doesn't matter what deductible you take. Here, our deductible is 0.25. This has nothing to do with D. This is always true for any D. Okay, this is a very, very special property which only holds for the exponential distribution in all the continuous distributions. So this has a special name. It's called the memory list because exponential distribution does not have memory. Okay, that's because of this result. Right, this is true for any D. Right? It doesn't matter how far away you are into this game. The probability that you will leave, for the next for the future is the same. So that's why we call this memoriness. It's convenient, but unlikely to be realistic in the modeling of risk. Okay. The next one is a lot more complicated. That is the reason why I use this specific video to handle this. Uh, One, it is mathematically challenging. Two, log normal is frequently tested on the SOA exam. So now let's analyze. By the way, the study is it's straightforward, right? We already derived the PDF for the log normal. So the tough part is here. How do you analyze the this integral, or how do you calculate this integral? Because the first identity is by definition, right? So if you want to calculate the expectation of YL, you just need to consider for all the loss greater than D to infinity, and then the positive part you can drop because now it's positive, right? It's strictly positive when Y is bigger than D. Then you times by the PDF of Y. You separate it into an integral and a constant part. This is D times the survival probability at D. The tough part is to analyze this integral. So first of all, you need to know the PDF of a log normal, which we have a few slides earlier on. So you can either apply your result from the formula, or you can do what I always do, is to apply the definition to go from y to the log y to calculate its density. So here will be negative log y minus mu taking square divided by 2 sigma square. So obviously y will be greater than 0, okay? So this is the density. So in order to solve, we basically we're trying to, right? So this y will cancel the y in the denominator. So I just write down the constant. And then we have this tough exponential to handle. That's the part, well, some of you may have trouble with. So the textbook directly give you the best transformation or the best change of variable, which it's not easy to see. From the calculus course, we know if you want to evaluate the integral and inside the integrand there is something complicated, you simply replace that complicated part. In this case, the complication comes from log y. So now let's use u to replace log y. If u is log y, I take exponential. Exponential of u will be y. So from here, I know eu du equals dy. Right? So basically, I apply differential on both sides. That's what I have. Now, okay, y goes from d to infinity, so u will go from log d to infinity. The constant stays. Exponential now becomes u minus v. Be careful, u and v somehow look similar. So now I replace dy. dy will be eu du. So now things look a lot nicer. You just need to open up the entire exponential term. So let's put it in exp. So I'm going to write out the factor, and I will open up this complete square. Remember, u is your argument. Mu is your constant. Mu and sigma are constants. Okay. We do have something outside. So let's bring it in. Okay, we need to divide by this, so it becomes negative 2 sigma squared times u. So basically, I bring this guy into everything inside the square bracket. Okay. The next technique I need is to complete the square. Okay, so now for the first order, I have mu plus sigma square. So what I want is, I want to get this into complete square. So that is the reason why I bring this term inside the square bracket, because it also has the first order term. So collect them together, it will be 2, put a bracket, mu plus sigma square, end bracket times u, right? So that's why I know here. But of course, I don't have the square for this guy. So the only thing I have is mu square. So we need to subtract the back 2 mu sigma square, subtract sigma to the fourth, then everything is the same. Okay. I have this term here, which is constant. Let's move it out. Okay, remember you need to divide it by negative 2 sigma square. So we have mu plus sigma the fourth will cancel the sigma square. I will have sigma square divided by 2. Okay, and what's inside? 1 over square root 2 pi sigma exponential. Let me write e, because you should be more familiar to see e right now. So it's u, let's put u back to x. Mu plus sigma square squared divided by 2 sigma square dx. Okay, what's inside? If you try harder to identify, that is actually the PDF of a normal distribution with mean mu plus sigma square with variance sigma square. Okay, so I can write this as 1 minus the, let's put a name for this. Let's call this n1. This will be 1 minus the CDF of n1 at log d. So this n1 is not a standard normal, so we need to standardize it. Okay, in order to standardize, we need to minus its mean divided by its z will be n1 minus its mean divided by its standard deviation. So divided by sigma, not sigma square. So then we convert to the standard normal. Log d minus mu minus sigma square divided by sigma. So textbook call this z star. Okay, then we have mu plus sigma square divided by 2 times 1 minus, we put this fancy phi, which is the CDF of a standard normal. Okay, you do have the table to get the value for this phi function. So that's why we convert to a standard normal. That's basically the technical part I want to show you. Once you get there, you can easily calculate this z star, which is about negative 1.88. You can plug in your normal table. I think it only goes to 2 digits, so you may want to either approximate to the closest one. If you want, you can do linear interpolation, right? It is between 1.88 and 1.89. So if you want, you can get the linear interpolation, but it's really not needed. You can just go to the nearest number you can find from the table and then get the value. This is likely to be computed by a software like R or MATLAB. Once you have this number, then it's nice because that gives you the integral. The second part is easy, right? The second part is to calculate this survival probability. All you need to do is to follow the same idea, but please don't need to You don't need to repeat, right? You already know most what you want. You just need to convert it, right? So what I mean is, by definition, and then there's no formula from here. We need y to be greater than d, right? And the y is a positive number, d is a positive number, which means I can take the logarithm. So let's put log greater than log d. Okay, by definition, y is log normal, log y is normal. But the mean, I need to convert it by standardization. Right, so we have this result. Okay, again, check the table, you will get the probability. Finally, you combine everything together to get the expectation of YL. Once you have YL, you divide by the survival probability. Luckily, we just computed, which is here. So you use it again. So that's the end of this example. Basically, for log normal, this is the, as I mentioned, the textbook use L. I often use LN, but please remember they are the same. Log normal is likely the most complete case we have. If you can handle log normal, you will be definitely fine for all other easier cases. Okay. By the end, I would like to introduce a concept which is called the loss elimination ratio. So this is the definition. From the name, we know it's between 0 and 1. Okay, that's because xl equals x minus d take positive, which is always less than or equal to y. So when we take expectation, the inequality sign will hold as well. So on top, you have something greater than 0, but less than the original expectation. So when you divide by it, of course, it will be between 0 and 1. That gives the name ratio. So most people would like to express it in percentage, but it's okay to keep in decimal. It's called loss elimination. Why it is called loss elimination? So let's take a look at the numerator. This is the expectation of the original loss or ground up loss. So this is the amount paid. So this is the amount paid. Of course, it's an expectation of the amount paid in a loss event. Okay, so this is the amount incurred. Of course, it's in a claim, it's in a loss event. Amount incurred and amount paid, there's a difference, right? So the difference is what you accomplish by introducing the deductible. So the difference is somehow the benefit to the insurance company, right? When you introduce this deductible, how much loss can you eliminate? And we always want to divide by the original amount of loss so that we get an idea in order to make comparisons across different scenarios. Otherwise, let's say let's consider like the home insurance, right? Of course, there are homes that worth like 100K, apartment. Let's say in Willimantic, there could be a fancy house, on top of a small hill in let's say in Glastonbury that could easily worth $1 million. So when you consider home insurance, one is 100K, the other one is 1,000K or $1 million. The impact of deductible, of course, will be hugely different, right? For a house this expensive, well, the deductible may not mean too much, right? But for this one, it could mean a lot. So that's why we need to somehow divide by the original expectation to unitize this result. That's why it's called the elimination ratio. And the ratio has the comparison purpose, right? We can compare for for houses with this much difference, right? If you study the ratio, but if you only consider the amount of elimination, then they may not mean too much, right? Because if you eliminate, let's say, 20K, well, it's 20% of this small apartment, right? But 20K is just the 2% of that mention. So when we, in that case, talking about actual amount has less meaning than talking about a ratio, right? A ratio is uniform. I will end here. In the next video, we will study the second modification limit and likely the third modification coinsurance.